Hey, welcome back. This time we're trying to figure out the surface area of these objects in 3 dimensions. And we will harken back to chapter 11 when we introduced area in terms of cross product. So there was one formula way back in the day that you've probably forgotten by now, but I made sure to put it on the first test. I remember that. So anyways, what are we doing? So let's develop the formula. Basically, we have some sort of surface, which I will attempt to draw. It's probably better just to look at the figure they have over there. But anyways, on this surface, you can, okay, so let's put it in some three-dimensional region. So you could consider kind of the shadow here, or you could work over top of this and then cross-section it into a bunch of little rectangles. And then at this particular point here, you can kind of trace that back up to the object. And so maybe it's sitting right here on the object. At that point, then you could create a tangent plane. And what they're going to do is use that the area of that tangent plane to do an approximation of the overall surface. So you can see there on the right, that picture 14.43. So I don't know why it was necessary for me to draw that, but there it is. This thing is what we're going to be adding up, right? So we want to add up all of those, all the areas of these little tangent planes, and that should approximate the sum of these actual little surface increments. So the tangent planes you see in dark blue and light blue, you see kind of a surface area increment. So for this rectangle in particular, you could kind of think of this side as change in x, and this side of the rectangle is a change in y. And then you could build vectors to describe that tangent plane over top of that point on the surface. So for the tangent plane then, we'll use two vectors. So vector u will be this x direction vector. So let me kind of put it in red here. So maybe sort of this part here would be u, and then we'll get a v for this part here. I mean, technically it should be over the point, but let's just pretend it's there in the middle. So anyways, so I'll have a change in the x direction for the first component. So it would be some change in x, and then 0 in the y direction, and then there is a rise or a fall in the z direction, right? And the rise or fall is based off of the derivative in the direction of x. In other words, the partial derivative with respect to x. So f sub x of whatever point you're dealing with. So you could say x sub I comma y sub I. Okay. So that point there, x sub I comma y sub I. Okay, then the other vector, you see that v vector I drew on this plane, we could describe 0 in the x direction, and then the y direction, some little change in y, and then the partial derivative with respect to y tells you kind of the either a rise or fall in that direction, right? So x sub I comma y sub I. And then we remember back to chapter 11, from chapter 11, the area of this tangent plane, which will be our delta t sub I, is from the cross product, right? It's the magnitude of the cross product of these vectors. And right, so I need to figure out the cross product first and then take the magnitude. I shouldn't have put the little symbols in. I just wanted to kind of remind you. So let me do the cross product first. So I, j, k over top. Hopefully you haven't forgotten how to do cross products. Delta x 0, fx 0, delta y, fy. And then this will be, of course, covering up the first column, getting the determinant of the leftover it'll be 0 minus fx delta y times all that times change in x. I mean all times, it's been a while. Okay. It's just that. Come on. I need to stretch out my room because I'm running out of room here. There we go. So that was a big issue. So it's that, and then cover up the second column. You'll get change in x times fy, and this of course is minus, negative, all of this minus 0, and then comma, cover up the last, and that would just be 0, right? So the magnitude then, simplifying this, negative x fx delta y, comma, fy, negative fy delta x, comma 0. The magnitude of u cross v is going to end up looking very, very familiar. Square root of 0. Shouldn't it be 1? Did I make a mistake? Yeah, I should have a 1 in there, it seems. I, j, and then... Oh, I see what I did. The third component is delta x delta y. Sorry. Delta x delta y. Sorry. Okay, so I'll have finding the magnitude delta x delta y squared plus f the partial squared times delta y squared plus the partial with respect to y squared times delta x squared. Then you could do some factoring and you'll get the square root of, let's factor out the delta x delta y squared, and you'll get 1 plus f sub x, and then I'm starting to think that I did this wrong as well. Yeah, so somehow I got a delta y where I didn't need. Okay, so for the first, you got to cover up this, and then it's fx times delta y. It's fx times. What did I screw up? Did I put it in wrong? Oh, I lost. That's what I did. Sorry. So these should be delta. There should be a delta x here because it's rise over run, but you only want the rise part, so you cross out the run part with the delta x, and then there should be a delta y here. Really? So there would be a delta x here, a delta y here, so this would be delta x, delta y, delta x, and so you would have all these would have delta y, delta x squares. So you could factor the delta x, delta y squares out of all three of those, and you just get 1 plus the partial with respect to x squared plus the partial with respect to y squared, and factoring it out you get a delta x delta y. And with the integral then you're adding these up all over the surface, so you would have the surface area equaling the double integral over the region of the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared dA. Okay. This formula looks strikingly similar to the arc length formula. If you remember, that was the square root of 1 plus f prime of x squared, okay, dx. And you could kind of remember it that way. So it's kind of just one level above the arc length. If you have the arc length formula, you have to have that memorized first. Okay. And they note that in the book. They say, oh, this looks really familiar. And where is that? Right here, this remark. Okay, so see how similar they are? Okay. All right. So there's a lot of formulas gonna come your way in chapter 15. Okay, so you want to start getting used to trying to figure out ways to memorize these things because they are a nightmare. Odds are on chapter 15 I'll give you a cheat sheet for the test, but um, I remember the first time I had to take like a comprehensive test in mathematics. You had to have these formulas memorized. I mean, they didn't give you anything. So yeah. Anyways, finding surface area then. So let's look at example 1. And yeah, if you didn't get it, this is the formula du jour for surface area. Okay, so example 1. Let's take a look. So generally, I want to figure out what the region looks like. I'm going to need the partial derivatives. So generally, I'll need to have my surface area solved for z. And sometimes that means, especially if you're dealing with like a sphere, you're going to have to kind of solve for z and get a square root function on one side and then use symmetry to get your integral to work out. Okay, but anyways, here is our formula. So let's get zx is just going to be -1, zy is just going to be -1, and so we'll have this region. We want the region above x squared plus y squared less than or equal to 1, which is a circle in the xy plane, everything inside the circle here. Okay. They only want it in the first quadrant though, so we are kind of right here integrating over that region. Okay, and that z function, that surface is a plane. So we may have forgotten how to draw planes. I will remind you really quick. This is x, this is y, this is z. So let x and y equal 0, z will be 2. So I'm working with this function here. Let z and x equal 0, so y will equal 2. And then let y and z equal 0, so x will end up equaling 2 if you solve for it. And that's kind of the plane that you're working with. You want to find the surface area of that over top of the circle x squared plus y squared equals 1, but only in the first quadrant. So the circle part is right here. Okay, so we want to find the surface area over top of that thing, and kind of projecting it onto that surface there. Attempting to project it. We'll kind of have this look to it, trying to find the surface area of this. Okay, right, so let's go to our integral, double integral, and we need the square root of 1 plus z sub x squared, which is 1, plus z sub y squared, which is 1. I'll go dy dx. So in the dy part, I'm going from y equals 0 to y equals the square root of 1 minus x squared. That's just from this equation solving for x, or solving for y, excuse me. And then on the x-axis, I'm going from 0 to 1, like that. So you'll have a square root of 3 from this business. That's just the square root of 3. I could factor that out of the integral. And then the integral of 1 dy will just be y. No, I don't think we really need to go the polar coordinates here. So I have y from 0 to, maybe I should have, 1 minus x squared dx. And then that will equal the square root of 3. I mean, technically, this region, what is this thing? It's just the area of that fourth of a circle. Okay, so this circle right here. So you kind of know what that's going to be. I mean, right now with the integral, it's not looking like a lot of fun. It looks like I'll probably have to do a u sub, trigonometric substitution. So what's better is to just literally think of this as the area of this and then evaluate that area using geometry. Okay, so what is the area of a circle? It's pi r squared. In this case, r is 1. So the area of that full circle is 1, and so the area of that part must be 1/4. So the answer would have been of that integral 1/4, so I get root 3 over 4. So if you could use geometry to get your integral done faster, definitely you want to do that. Whoops, I lost my pi over 4. So root 3 pi over, but that's the kind of careless mistake that can hang you up if you're really tired, right? So anyways, there's that. Let's look at the homework. So the homework is just more finding surface area problems, finding surface area, finding surface area, finding surface area. That's all they have in the examples here. So let's go to the homework and see what we're dealing with there. Some of these first ones, just finding the area over top of a box. It should be pretty quick and simple. You literally don't have to do the integral because you'll know the area, and the square root part will just be a constant with all probability. This guy, the square root, is not going. I don't think it's going to be a constant. So let's look at number 3 and see what we're in against. F of xy is 16 minus x squared, so fx is negative 2x. Fy, of course, is 0, and we have a square. Sides length 2, given by those points. So we have double integral of the square root from 0 to 2, 0 to 2, I'll go dy dx of 1 plus 4x squared plus 0 squared. And this nasty little critter does not look like a lot of fun, right? So that thing right there, it's not going to be possible to get it in terms of like a circle and then use geometry. You can't do that. You're literally going to have to do a trig sub. I hate to say it, folks, but 2x would be tan theta, x would be tan theta over 2, and then dx would be secant squared theta d theta all over 2. And if we need to convert back, I need my triangle. So opposite is, I should have solved for theta, right? Let me solve for theta first. So theta will be tan inverse of 2x. So I get my triangle. There's my theta. So opposite over adjacent, and then 4x squared plus 1. Okay. All right, so this would be the double integral of the square root of 1 plus tan squared theta times secant squared theta all over 2 d theta dx. Okay, what a nightmare. Maybe it would have been better to do the other order of integration. Yeah, it would have. It would have been so much easier. Let's do the other order of integration, shall we? Because I think it's going to be easier, right? So if I have a square root of 1 plus 4x squared and then dx. Oh, and I was doing it in the correct order, right? dy dx would be the way to go. Because when you integrate first, you're just going to get y times the square root of 1 plus 4x squared, evaluated from 0 to 2. Well, you're still going to be in the same boat. All right, I apologize. I thought I was on to something there. Okay, sorry about that. So anyways, carrying right along. So I have the square root of 1 plus tan squared theta times secant squared theta all over 2 d theta dx. And I'm trying to figure this out. That'll be the integral of, I could factor out 1/2, and then the square root of 1 plus tan squared, that's going to be the square root of secant squared, which will just be secant, and then I end up with a secant cubed theta d theta. Believe it or not, I've done that integral so many times, I kind of know what it is. It is secant theta tan theta all over 2, and then it's either minus or plus. So, I mean, you would have to do like a by parts on it. Okay, it's either going to be minus or plus. I can't remember if it's minus or plus. So You would have like a u is your secant, and then dv is secant squared. So v is tan, and then du is sec tan. So it's going to be this times this minus the integral of this times this. So there would be like a tan squared. I bet it's minus. So minus ln absolute value of secant theta plus tan theta. You could always look that up in the tables in the book, or just use a calculator to get it. And I'm still integrating this guy with respect to x after I get done with this junk. Okay, so this guy, I'm going to factor out another 1/2, so I get a 1/4 out in front of everything. Secant then is 1 over cosine, right? So that'd be adjacent all over. And I bet it's plus because I could see the answer says plus, but hold on. It's going to be adjacent over hypotenuse, so square root of 4x squared plus 1 times tan, which is opposite over adjacent. Oops, the first one is hypotenuse over adjacent. I apologize. So this is square root 4x squared plus 1 over 1. I guess I don't need to write the over 1 parts. And then I'm betting this is going to end up being a plus. ln of sort of the same thing, right? So the square root of 4x squared plus 1 plus 2x, and then dx. But I need to evaluate that thing. It should all have been in terms of y, right? So yeah, sorry about that. So I'm just butchering this problem. I apologize. So this will be dy dx, and then no, dx dy. So this will be dy here. Sorry. All right. So that's there's a dy sitting on the outside. And I'm evaluating from 0 to 2 on there, so it'd be 1/4 integral of square root of 17 times 4 plus ln of 17 plus 4 minus plugging in 0. You just get 0 plus ln of 1, which is 0. Dy, and all of this junk is just a constant, so you could factor it out. Multiply by 1/4, you get square root 17. Well, I may want to. So square root 17 plus ln of 21 times the integral of dy from 0 to 2. What's square root 17 in here? So I can't simplify that. Square root Charlie. I'm 17 plus 4. Okay, and then that's going to be square root of 17 plus ln of the square root of 17 plus 4 times y, evaluated from 0 to 2, and that's going to put a 2 in there. So at the end of the day, it's just going to be 2 times the square root of 17 plus ln of the square root of 17 plus 4. And yeah. Okay, so a bit nasty integral. Sorry about butchering it there in the beginning. Dx dy. Then I had to do a trig sub. I have this part memorized because it comes up so much in my teaching. You would probably have to look it up in the book. Anyways, it comes down to this integral. You can do by parts, and then it turns into a looper, and you have to solve for the integral. It's annoying. It just turns into this though. And then you back sub using the triangle. So secant of theta, remember, is 1 over cosine. So it's hypotenuse over adjacent, square root of 4x squared plus 1 times tan of theta. Tan is opposite over adjacent, so 2x over 1, and then plus ln of the same stuff, but added, right? So then I evaluated this thing from 0 to 2. If you plug in 2, you'll have in here 4, and then in here you have square root of 2 squared is 4. 4 times 4 is 16, plus 1 is 17. So root 17 times 4. And then this would be root 17, and this would be 4 as well. Okay, and then if you put in 0, this part here would be 1, square root of 1, but this part here would just be 0, so that'll turn to 0. You plug 0 into the second part. This part would be the square root of 0 plus 1, which is square root of 1, which is 1. This part would be 0, so you'd have 1 plus 0. ln of 1 is just 0, so that part became this. And then I was able to factor this out of the integral, multiply it by 4, that's this part right here, and then finally integrate 1 dy. Okay, so kind of annoying, and that's why you see you got this really butchered answer, 2 square root 17. Okay, I'm presuming that number 4 is just as ugly and nasty. Let's try number 5er. Okay, so number 5. The surface area above the region, and they're giving us f is 3 plus 6x to the 3 halves. Okay, so I need fx. That's going to be 6 times 3 halves. X to the 3 halves minus 2 halves is 1 halves. So this would be 9 halves x to the 1 half. Fy would be 0, and then I'm integrating over top of 0, 0, 0, 2, and then 6, 2. Okay, so this box, and again I have a double integral. I want to do so I got the square root of 1 plus 81 fourths x. And then I guess I'll do dx and then dy. Oh, this won't be too bad. Okay. So integrating with respect to x first. Let's get the bounds as well. The limits, rather. My u sub is going to be 1 plus 81 fourths x. So du would give me 81 fourths dx. And so I'm going to have this factor of 481ths floating around. So I could factor that out of the integral, 4 over 81, integral of the integral of u to the 1 half du, and then our dy. So this will be 4 over 81. Integrating u to the 1 half, I get u to the 1 half plus 2 halves is 3 halves times 2/3. Let's put the 2/3 on the outside. And then I need to evaluate this eventually after I back sub. On the outside, then, I'm getting 8 all over 273 times the integral of 1 plus 81 fourths to the 3 halves, evaluated from 0 to 6, then dy. So I have 8 all over 273 times the integral of, and there should be an x on this, I apologize, of 1 plus 81 times 6 all over 4 to the 3 halves. Ain't that nice of them? And then you have to also evaluate it at 0. Usually it's just 0, and that is the integral killer, because you'll forget to subtract this other part and it'll ruin your answer. But if you plug 1 in for x, you're just going to get 1 plus 0, which is 1, and then 1 to the 3 halves is just 1. Okay, so you get that nasty bit. And then dy. Simplifying a little bit, so what do we have? 2 over, or rather 3 all over 2. So this will be 1 plus 273 all over 2 to the 3 halves minus 1. And then 2 halves plus 273 halves is 275 halves to the 3 halves minus 1. That whole thing is a constant that can be pulled out of the integral. So you're going to be having 8 all over 273 times 275 halves raised to the 3 halves minus 1 times the integral of dy. And of course that'll be 8 all over 273 times 275 all over 2 to the 3 halves minus 1 times y evaluated from 0 to 2. Plugging in a 2, and you get 16 in the numerator, which totally seems wrong. I missed a 1/2 somewhere or something. Let me pause the video and find my mistake. And as luck would have it, the mistake is at the beginning. Right here should be 6 times 3 halves. So 2 goes in the 6 3 times, and 3 times 3 is 9. So this would just be 9. This would just be 81. This would be, my eye itches, 1 over 81. This would be 1 over 81. This will be 1 over 81. This will be 81 over 1. This will be 1. This will be, so redoing this one then, 81 times 6. So you have 6 and then 48 plus 1 is 487. So this is 487 to the 3 halves instead. So this will be 1 plus 487 to the 3 halves minus 1, or rather 1 plus 486. And then when I added that together, it's 487 to the 3 halves minus 1. So this will become then 1 over 273, and then we have 487 to the 3 halves minus 1. Okay, get rid of that chunk. So this is 1 all over 273. This is 487. And then multiplying by 2, you get the right answer. Okay, so this will end up being 2 all over 273 times 487 to the 3 halves minus 1, and that's your answer. Okay, so kind of nasty, like I said. Not a lot of fun. Sadly. Let's look at number 6. See if I can fumble my way through this one. So our function this time is ln of secant, and the region we're integrating over, let's make this the video quiz while we're at it. So this will be the first video quiz in video quiz set number 8, problem 6 from WebAssign. All right, so the region I'm working with 0, x is in between 0 and pi over 4, and then y is in between 0 and tan. Looks like a real nightmare. And let's see what that region looks like. So 0 to pi over 4 is that wedge, and then y equals 0, of course the x-axis to y equals tan. It's this region right here that I'm trying to find the I'm integrating over that region. I'm trying to find the surface area of this thing over top of this region that I just drew out. Okay, so I need fx. That'll be 1 all over secant x times secant x tan x. So it's just going to be tan x. And then, of course, fy will be 0. So I have the double integral of the square root of 1 plus tan squared x plus 0 squared. And then I'll do, I guess, dx dy, or dy dx should be. Probably dy dx better. I do dy dx because I know that then I could get the outer bounds. It's going to be pretty simple, and I'm not going to have to worry about inverse functions. But I'm going curve the curve, so y equals 0 to y equals tangent. And then point to point, so x equals 0 to x. It may not even be possible to do it in this order, but we'll see, right? Okay, so 1 plus tan squared is very simply just secant squared x. And then I do the square root of that. That'll just give me a secant. So double integral of secant x dy dx, integrating with respect to y. That's just going to give me y times secant x from 0 to tan x. This ain't so bad. Don't know why I picked this one. Plugging in tan x, I get tan x secant x, and then minus 0 dx. And then the integral of tan secant is just secant x, 0 to pi over 4. And then, of course, secant of pi over 4 is root 2. Secant of 0 is 1. Well, that was quite easy. So that was our video quiz, unfortunately. Hate to make them that easily. Anyways, there's that. Okay. What's next? So finding above, area above. Above. Let's try number 11. So this one, for some of these, you really got to get the picture, right? So, you have your x squared plus y squared plus z squared equals 625, and that's a sphere, a huge sphere. And then x squared plus y squared equals 49 is a cylinder. So basically you have a cylinder going through a sphere, and thinking about what that looks like, you have the hole where the cylinder is popping up through the top of it. I should draw it a little better. Okay. And then going down through the bottom. So what do they want the surface area of, right? The portion of the sphere inside the cylinder, x squared plus y squared is 49. So what they're looking for are basically these portions in here. They're kind of like little contact lenses. They want this surface, the surface area of that part, and then also the downward part. Okay, so down here, they also want then this portion. Okay, so what I'm going to do is, this is one of those ones where I say you kind of have to split it in half and use symmetry, because I always need that formula for f of x in terms of f of xy. So z squared is 625 minus x squared minus y squared, and then z will be plus or minus the square root, but I'm just going to kind of multiply my integral by 2 in order to get the other surface area. So there's like surface area 1 here and then surface area 2. I'm only going to be able to get one of those because of the way we had to kind of form our function f of xy. Okay, so I got to get the partials. Zx is going to be power rule will give you a 1/2 all over, okay, all of its glory. 1/2 times 625 minus x squared minus y squared to the negative 1/2 times negative 2x. So that's going to be negative x all over the square root of 625 minus x squared minus y squared. Zy is going to be the same thing, but with a y on top. So that would be square root of 625 minus x squared minus y squared. Then I'm going to put it in my integral. And also I have to think of what am I integrating over top of, right? So here is my sort of XYZ thingamajig, and inside here the story problem is telling me to integrate over this circle. X squared plus y squared equals 49, right? So that has radius 7, but in the xy plane, if you want to think of it there, it's this circle. And you may even want to just cut that into a fourth, and then at the end you'll multiply the entire integral by 8, right? Because you're going to get 4 pieces for S1, 4 pieces for S2, and that may be easier. Let's do that, right? So I'm just going to figure out the area over top of this and then multiply it by 8. Okay, so 8, I'm going from y equals 0 to y equals the square root of 49 minus x squared. And that formula just comes from this inner circle formula. X squared plus y squared is 49. Right, and then I'm going from 0 to 7 on the x-axis. And then my square root thingamajig is going to be 1 plus zx squared is x squared all over 625 minus x squared minus y squared, plus y squared all over 625 minus x squared minus y squared. And then I'm going to go some order. This dy dx is what I specified. Y equals 0 to y equals square root of 49 minus x squared, x equals 0 to x equals 7. Okay, so I have 8 times the integral, double integral. We're going to find a common denominator here, so it would be 625 minus x squared minus y squared on the first guy, plus x squared over that common denominator. And hopefully that will simplify at least a little. Sometimes the square root will completely go away, but here, what are you getting? You're getting the square root of, it looks like just 625 all over 625 minus x squared minus y squared dy dx. Square root of 625, what the heck is that? 625 square root of is 25. Okay, so I could pull out a 25 times 8, whatever the heck that is. 25 times 8, I think it's like 200. Double integral of 625 minus x squared minus y squared to the negative 1/2. I have to go the polar coordinates for that. That is too much nonsense for me, the stomach. So 200 double integral r equals 0 to r equals 7. I'm only going to pi over 2. And then I have 625 minus r squared times r dr d theta. So there's another r sitting right there. Dr d theta. 200. I'm going to have to do a u sub on this. 625 minus r squared du will give you negative 2r dr. So there's going to be a negative 1/2 coming out in front. So negative 2 onto that. So our u to now the negative 1/2, and then du d theta. Power rule. Got a negative 100 in front. So I get u to now the negative 1/2 plus 1/2. Negative 1/2 plus 1 is negative 1/2 plus 2/2, which is 1/2. Divided by 1/2 is times 2, so this will become 200 in front. And then I need to evaluate once I back sub. So this will be negative 200 integral of 625 minus r squared to the 1/2 from 0 to 7, I think we decided on. And then d theta. So this will be negative 200, and then I have 625 minus 49. It's 576. 576 And this is another one where you could really screw up. It's 576 to the 1/2, but then you have to remember to plug in 0 as well, because you're so used to thinking that when I plug in 0, it's all going to be 0. No. So anyways, then that would be 625 to the 1/2 minus 0. 625 minus 0, which is a 625, 625 to the 1/2. That'll give you a 25 d theta. You can factor that out the front, so get negative 200 times 576 to the 1/2 minus 25. And then you have the integral of d theta from 0 to the pi over 2. And it looks like I nailed this one. So negative 200 times 576 to the 1/2 minus 25 theta from 0 to the pi over 2. So that would be negative 200 pi over 2 is negative 100 pi times 576 to the 1/2 minus 25. There's your answer. That last one, again, it's a good idea to, I'll do this one last one and cut it. It's a good idea to figure out what the heck it is you're looking at, right? So we have this cone, z equals 2 square root of x squared plus y squared, and we want to know the surface area of that cone inside the cylinder. Okay, so you're going to have a cylinder, x squared plus y squared is 36, okay, and then there's this cone inside of it. Okay, so you're basically integrating over this circle in the xy plane. X squared plus y squared is 36. I need my partials. So zx, 2 times 1/2 times x squared plus y squared, now to the negative 1/2 times 2x, which is just 2x all over the square root of x squared plus y squared. Zy, same thing but with a y. And then you dump that into your integral, and you're integrating over top of this circle. Again, you could kind of cut it into pieces. I'm not going to play that game this time. I'm going to actually probably convert to polar, so I'm not even going to bother indicating my integral limits. So I just put an R there. So inside here I'll have 1 plus 4x squared all over x squared plus y squared plus 4y squared all over x squared plus y squared. Then you need to get a common denominator. Double integral of the square root of well, the common denominator for 1 is going to be x squared plus y squared all over x squared plus y squared. And then plus 4x squared all over x squared plus y squared. And then plus 4y squared all over x squared plus y squared, all in the radical. And then you're going to add them all up. So you get 4x squared plus x squared is 5x squared plus 5y squared all over x squared plus y squared. And this turns out real nice. So you're getting the double integral of, if you factor out the 5 in the numerator, you're just going to get square root 5. Okay. So the surface area is just square root 5 times that area that I'm integrating over, which was a circle. So the area of that circle is pi times r squared. R is 6. So it's just 36 pi for that integral. So this will equal 36 pi square root 5. Okay. And you see that's the answer. So yeah, some of these integrals can be really annoying, but yeah, there you have it. Okay, thank you for watching as usual, and I will see you next time.